A few months ago, the Nobel Prize in Physics was awarded to two teams of astronomers for a discovery that has been hailed as one of the most important astronomical observations ever. And today, after briefly describing what they found, I'm going to tell you about a highly controversial framework for explaining their discovery, namely the possibility that way beyond the Earth, the Milky Way, and other distant galaxies, we may find that our universe is not the only universe, but is instead part of a vast complex of universes that we call the multiverse. Now, the idea of a multiverse is a strange one. I mean, most of us were raised to believe that the word universe means everything. And I say most of us with forethought, as my 4-year-old daughter has heard me speak of these ideas since she was born. And last year, I was holding her and I said, "Sophia, I love you more than anything in the universe." And she turned to me and said, "Daddy, universe or multiverse?" But barring such an anomalous upbringing, it is strange to imagine other realms separate from ours, most with fundamentally different features, that would rightly be called universes of their own. And yet, speculative though the idea surely is, I aim to convince you that there's reason for taking it seriously, as it just might be right. I'm going to tell the story of the multiverse in 3 parts. In part 1, I'm going to describe those Nobel Prize-winning results and highlight a profound mystery which those results revealed. In part 2, I'll offer a solution to that mystery. It's based on an approach called string theory, and that's where the idea of the multiverse will come into the story. Finally, in part 3, I'm going to describe a cosmological theory called inflation, which will pull all the pieces of the story together. Okay, part 1 starts back in 1929 when the great astronomer Edwin Hubble realized that the distant galaxies were all rushing away from us, establishing that space itself is stretching, it's expanding. Now, this was revolutionary. The prevailing wisdom was that on the largest of scales, the universe was static. But even so, there was one thing that everyone was certain of. The expansion must be slowing down. That is, much as the gravitational pull of the Earth slows the ascent of an apple tossed upward, the gravitational pull of each galaxy on every other must be slowing the expansion of space. Now let's fast forward to the 1990s, when those two teams of astronomers I mentioned at the outset were inspired by this reasoning to measure the rate at which the expansion has been slowing. And they did this by painstaking observations of numerous distant galaxies, allowing them to chart how the expansion rate has changed over time. Here's the surprise. They found that the expansion is not slowing down. Instead, they found that it's speeding up, going faster and faster. That's like tossing an apple upward, and it goes up faster and faster. Now, if you saw an apple do that, you'd want to know why. What's pushing on it? Similarly, the astronomers' results are surely well deserving of the Nobel Prize, but they raised an analogous question. What force is driving all galaxies to rush away from every other at an ever-quickening speed? Well, the most promising answer comes from an old idea of Einstein's. You see, we are all used to gravity being a force that does one thing: pulls objects together. But in Einstein's theory of gravity, his general theory of relativity, gravity can also push things apart. How? Well, according to Einstein's math, if space is uniformly filled with an invisible energy, sort of like a uniform invisible mist, then the gravity generated by that mist would be repulsive. Repulsive gravity, which is just what we need to explain the observations, because the repulsive gravity of an invisible energy in space, we now call it dark energy, but I've made it smoky white here so you can see it. Its repulsive gravity would cause each galaxy to push against every other, driving the expansion to speed up, not slow down. And this explanation represents great progress. But I promised you a mystery here in part one. Here it is. When the astronomers worked out how much of this dark energy must be infusing space to account for the cosmic speedup, look at what they found. This number is small. Expressed in the relevant units, it is spectacularly small. And the mystery is to explain this peculiar number. We want this number to emerge from the laws of physics, but so far, no one has found a way to do that. Now, you might wonder, should you care? Maybe explaining this number is just a technical issue, a technical detail of interest to experts, but of no relevance to anybody else. Well, it surely is a technical detail, but some details really matter. Some details provide windows onto uncharted realms of reality, and this peculiar number may be doing just that, as the only approach that so far made headway to explain it invokes the possibility of other universes, an idea that naturally emerges from string theory, which takes me to part two, string theory. So hold the mystery of the dark energy in the back of your mind as I now go on to tell you three key things about string theory. First off, what is it? Well, it's an approach to realize Einstein's dream of a unified theory of physics, a single overarching framework that would be able to describe all the forces at work in the universe. And the central idea of string theory is quite straightforward. It says that if you examine any piece of matter ever more finely, at first you'll find molecules, and then you'll find atoms and subatomic particles. But the theory says that if you could probe smaller, much smaller than we can with existing technology, you'd find something else inside these particles. A little tiny vibrating filament of energy, a little tiny vibrating string. And just like the strings on a violin, they can vibrate in different patterns, producing different musical notes. These little fundamental strings, when they vibrate in different patterns, they produce different kinds of particles. So electrons, quarks, neutrinos, photons, all other particles would be united into a single framework as they would all arise from vibrating strings. It's a compelling picture, a kind of cosmic symphony where all the richness that we see in the world around us emerges from the music that these little tiny strings can play. But there's a cost to this elegant unification, because years of research have shown that the math of string theory doesn't quite work. It has internal inconsistencies unless we allow for something wholly unfamiliar: extra dimensions of space. That is, we all know about the usual 3 dimensions of space, and you can think about those as height, width, and depth. But string theory says that on fantastically small scales, there are additional dimensions crumpled to a tiny size, so small that we have not detected them. But even though the dimensions are hidden, they would have an impact on things that we can observe, because the shape of the extra dimensions constrains how the strings can vibrate. And in string theory, vibration determines everything. So particle masses, the strengths of forces, and most importantly, the amount of dark energy would be determined by the shape of the extra dimensions. So if we knew the shape of the extra dimensions, we should be able to calculate these features, calculate the amount of dark energy. The challenge is, we don't know the shape of the extra dimensions. All we have is a list of candidate shapes allowed by the math. Now, when these ideas were first developed, there were only about 5 different candidate shapes, so you could imagine analyzing them one by one to determine if any yield the physical features we observe. But over time, the list grew as researchers found other candidate shapes. From 5, the number grew into the hundreds and then the thousands. A large but still manageable collection to analyze, since, after all, graduate students need something to do. But then the list continued to grow into the millions and the billions, until today, the list of candidate shapes has soared to about 10 to the 500. So, what to do? Well, some researchers lost heart. concluding that with so many candidate shapes for the extra dimensions, each giving rise to different physical features, string theory would never make definitive testable predictions. But others turn this issue on its head, taking us to the possibility of a multiverse. Here's the idea. Maybe each of these shapes is on an equal footing with every other. Each is as real as every other in the sense that there are many universes, each with a different shape for the extra dimensions. And this radical proposal has a profound impact on this mystery, the amount of dark energy revealed by the Nobel Prize-winning results, because you see, if there are other universes, and if those universes each have, say, a different shape for the extra dimensions, then the physical features of each universe will be different, and in particular, the amount of dark energy in each universe will be different, which means that the mystery of explaining the amount of dark energy we've now measured would take on a wholly different character. In this context, the laws of physics can't explain one number for the dark energy because there isn't just one number. There are many numbers, which means we have been asking the wrong question. Instead, the right question to ask is, why do we humans find ourselves in a universe with the particular amount of dark energy we've measured instead of any of the other possibilities that are out there? And that's a question on which we can make headway, because those universes that have much more dark energy than ours, whenever matter tries to clump into galaxies, the repulsive push of the dark energy is so strong that it blows the clump apart and galaxies don't form. And in those universes that have much less dark energy, well, they collapse back on themselves so quickly that, again, galaxies don't form. And without galaxies, there are no stars, no planets, and no chance for our form of life to exist in those other universes. So we find ourselves in a universe with the particular amount of dark energy we've measured simply because our universe has conditions hospitable to our form of life. And that would be that. Mystery solved, multiverse found. Now, some find this explanation unsatisfying. We're used to physics giving us definitive explanations for the features we observe. But the point is, if the feature you're observing can and does take on a wide variety of different values across the wider landscape of reality, then seeking one explanation for a particular value is simply misguided. An early example comes from the great astronomer Johannes Kepler, who was obsessed with understanding a different number, why the sun is 93 million miles away from the Earth. And he worked for decades trying to explain this number, but he never succeeded, and we know why. Kepler was asking the wrong question. We now know that there are many planets at a wide variety of different distances from their host stars, so hoping that the laws of physics will explain one particular number, 93 million miles, well, that is simply wrong-headed. Instead, the right question to ask is, why do we humans find ourselves on a planet at this particular distance instead of any of the other possibilities? And again, that's a question we can answer. Those planets which are much closer to a star like the sun would be so hot that our form of life wouldn't exist. And those planets that are much farther away from the star, well, they're so cold that, again, our form of life would not take hold. So we find ourselves on a planet at this particular distance simply because it yields conditions vital to our form of life. And when it comes to planets and their distances, this clearly is the right kind of reasoning. The point is, when it comes to universes and the dark energy that they contain, it may also be the right kind of reasoning. One key difference, of course, is we know that there are other planets out there, but so far I've only speculated on the possibility that there might be other universes. So to pull it all together, we need a mechanism that can actually generate other universes. And that takes me to my final part, part 3. Because such a mechanism has been found by cosmologists trying to understand the Big Bang. You see, when we speak of the Big Bang, we often have an image of a kind of cosmic explosion that created our universe and set space rushing outward. But there's a little secret. The Big Bang leaves out something pretty important: the bang. It tells us how the universe evolved after the bang, but gives us no insight into what would have powered the bang itself. And this gap was finally filled by an enhanced version of the Big Bang theory. It's called inflationary cosmology, which identified a particular kind of fuel that would naturally generate an outward rush of space. The fuel is based on something called a quantum field, but the only detail that matters for us is that this fuel proves to be so efficient that it's virtually impossible to use it all up, which means in the inflationary theory, the Big Bang giving rise to our universe is likely not a one-time event. Instead, the fuel not only generates our Big Bang, but it would also generate countless other Big Bangs, each giving rise to its own separate universe, with our universe becoming but one bubble in a grand cosmic bubble bath of universes. And now, if we meld this with string theory, here's the picture we're led to. Each of these universes has extra dimensions. The extra dimensions take on a wide variety of different shapes. The different shapes yield different physical features, and we find ourselves in one universe instead of another simply because it's only in our universe that the physical features, like the amount of dark energy, are right for our form of life to take hold. And this is the compelling but highly controversial picture of the wider cosmos that cutting-edge observation and theory has now led us to seriously consider. One big remaining question, of course, is, could we ever confirm the existence of other universes? Well, let me describe one way that might one day happen. The inflationary theory already has strong observational support because the theory predicts that the Big Bang would have been so intense that as space rapidly expanded, tiny quantum jitters from the micro world would have been stretched out to the macro world, yielding a distinctive fingerprint, a pattern of slightly hotter spots and slightly colder spots across space, which powerful telescopes have now observed. Going further, if there are other universes, the theory predicts that every so often, those universes can collide. And if our universe got hit by another, that collision would generate an additional subtle pattern of temperature variations across space that we might one day be able to detect. And so exotic as this picture is, it may one day be grounded in observations establishing the existence of other universes. I'll conclude with a striking implication of all these ideas for the very far future. You see, we learned that our universe is not static, that space is expanding, that expansion is speeding up, and that there might be other universes, all by carefully examining faint pinpoints of starlight coming to us from distant galaxies. But because the expansion is speeding up, in the very far future, those galaxies will rush away so far and so fast that we won't be able to see them, not because of technological limitations, but because of the laws of physics. The light those galaxies emit, even traveling at the fastest speed, the speed of light, will not be able to overcome the ever-widening gulf between us. So astronomers in the far future, looking out into deep space, will see nothing but an endless stretch of static, inky, black stillness. And they will conclude that the universe is static and unchanging and populated by a single central oasis of matter that they inhabit, a picture of the cosmos that we definitively know to be wrong. Now, maybe those future astronomers will have records handed down from an earlier era, like ours, attesting to an expanding cosmos teeming with galaxies. But would those future astronomers believe such ancient knowledge? Or would they believe in the black, static, empty universe that their own state-of-the-art observations reveal? I suspect the latter, which means that we are living through a remarkably privileged era when certain deep truths about the cosmos are still within reach of the human spirit of exploration. It appears that it may not always be that way, because today's astronomers, by turning powerful telescopes to the sky, have captured a handful of starkly informative photons, a kind of cosmic telegram, billions of years in transit, and the message echoing across the ages is clear. Sometimes, nature guards her secrets with the unbreakable grip of physical law. Sometimes, the true nature of reality beckons from just beyond the horizon. Thank you very much.
Brian, thank you. The range of ideas you've just spoken about are dizzying, exhilarating, incredible. How do you think of where cosmology is now in a sort of historical side? Are we in the middle of something unusual historically, in your opinion?
Well, it's hard to say. When we learn that astronomers of the far future may not have enough information to figure things out, the natural question is, maybe we're already in that position, and certain deep, critical features of the universe already have escaped our ability to understand because of how cosmology evolves. So from that perspective, maybe we will always be asking questions and never be able to fully answer them. On the other hand, we now can understand how old the universe is. We can understand how to understand the data from the microwave background radiation that was set down 13.72 billion years ago, and yet we can do calculations today to predict how it will look, and it matches. Holy cow, that's just amazing. So on the one hand, it's just incredible where we've gotten, but who knows what sort of blocks we may find in the future.
You're going to be around for the next few days. Maybe some of these conversations can continue. Thank you.
My pleasure.
Thank you.
Much.
Thank you, Brian.